Thanks for watching. So this is joint work with Frank at UC Berkeley and Adam, Rocco and Chen at Columbia. So I'll talk about population recovery from the deletion channel. Before introducing that problem though, I'll talk about a simpler problem which is called trace reconstruction. In this problem, you are given some unknown n-bit string. So for example, the string on the right, and then you get corrupted samples from this string where the corruption happens by deleting some bits. So here's an example. I start with the string x, and then let's say the first bit is transmitted with as it is, the second bit as well, but then the third bit is deleted, and then I get the fourth bit of the original string as the third bit in my sample. And so the model is basically each bit is deleted independently with some probability delta, let's say 1/4. And the surviving bits are concatenated and returned as a sample. And this is what it looks, a sample looks like, and these samples we'll call as traces. And so we get a bunch of independent traces from this deletion channel using this process. And the goal is to recover the original string with high probability from the traces we receive. And in this talk, we'll just focus on sample complexity. There's the number of traces we need to recover the string. We won't worry too much about the computational runtime of the algorithms. So I won't talk too much about motivation, but one of the main one of the main places where trace reconstruction is actually used in practice is for reconstructing DNA sequences of ancestral species from DNA sequences of species that we have today if you model mutations as sort of insertions, deletions, and substitutions which happen independently. And it turns out that deletions are the hardest case, so we focus on that. Okay, so it should be intuitively clear that this is a significantly harder form of corruption than substitutions or erasure channels, because we don't know, for a given bit in the trace, we don't know which bit it corresponds to in the original string. We don't have the synchronization that is there in other corruption channels. And indeed, the upper bound results that we know currently reflect that. The best known upper bound sample complexity for recovering a string from the deletion channel is exponential in n to the 1/3 by simultaneous works of Day, O'Donnell, and Servedio, and Nazarov and Perez 2 years ago. And this is they give something called a mean-based algorithm, and they also show that their bounds are the best for any mean-based algorithms. I won't really get into that, what mean-based algorithms are, but in terms of general lower bounds, we have an exponential gap between upper and lower bounds. The best lower bound on this problem, when the original string is arbitrary, is only polynomial, n to the 3/2. In the average case, when the original string is a uniformly random n-bit string, we can do significantly better. Holden, Pimentel, and Perez showed that you can reconstruct the original string with high probability using subpolynomial number of traces. So, exponential in log n to the 1/3 traces is good enough. And lower bounds that Chase gave for the worst case also translate to some lower bounds in this average case, where the lower bound is log n to the 5/2. So again, we have an exponential gap between the upper and lower bounds in the average case. So now we'll consider generalization of this problem, and this is the focus of this work, which we call population recovery with deletions. Now instead of one source string, you have L source strings and some unknown distribution over them. So here I've given an example with L equal to 3 and some distribution over the strings. And now the sample generation process is as follows. Each time we draw one of the strings with the associated probability. So here, suppose I draw the second string in my support with probability 0.3, and then I pass this through the deletion channel. So this would delete each bit with probability 1/4 independently, and I get the surviving string back. By the way, the constant 1/4 is not really important. Any constant less than 1 is sort of equivalent in terms of hardness. So the goal is to get this mixture of traces from this population and to recover all the strings, at least all the strings which occur with probability at least epsilon, and the weights of the distribution up to small error, so up to total variation distance epsilon. Yeah, just to reiterate, the trace reconstruction corresponds to the population recovery problem for the special case when L is equal to 1. Okay, so population recovery has been studied in other models like substitution and erasure a lot. So there's a long line of works that for these other models where, so now we basically know like optimal sample complexity upper and lower bounds for these channels, and if the support size of the distribution is known, then we basically have algorithms which run in polynomial time in all relevant parameters. On the other hand, for the deletion channel, there's not really much prior work. We considered this deletion channel problem in the average case when the strings x1 through xl in the support are random, but the distribution over them, the mixing weights, that's still arbitrary. In this average case version, we can show an efficient algorithm which has sample complexity polynomial in the support size and like sub polynomial in the length of the strings using, so this is, so the high level approach of this algorithm is to sort of reduce to the algorithms for average case trace reconstruction using a clustering procedure. So basically, given a mixture of traces, we can sort of efficiently figure out for any pair which whether they came from the same string or for different strings. And this works out because average random strings differ a lot. Two independent random strings differ a lot. So and even their traces will differ a lot, and this is why we get the average case efficient algorithm. However, so now we are back to this work which considers worst case strings and worst case distributions over them. And in this case, two different strings can differ in only one bit. So two strings can be very close, and it's not clear that that kind of clustering procedure would work. And indeed, we don't do that kind of clustering procedure. We give a completely new approach. So here are main results. We show that any distribution over L strings, L is known, the support size is known. Any distribution over L strings can be reconstructed up to total variation distance epsilon using 1 over epsilon squared times this bound, which is exponential in root n and doubly exponential in L, the support size. And we have some lower bounds for this problem. We show that for any L which is slightly smaller than root n, we need at least n to the L samples to recover the population up to TV distance some constant epsilon, let's say 0.01. Okay. So in this talk, I'll only have time to talk about the upper bound. Before giving the algorithm for sample complexity result for population recovery, I'll show a 2 to the root n upper bound for trace reconstruction. If you recall, 2 to the root n is not optimal for trace reconstruction. We have a 2 to the n to the 1/3 algorithm. However, the algorithm there is mean based and completely fails even for population recovery, even for distributions with just 2 strings and uniform distribution over them. Whereas this technique will generalize in a non-trivial way. So I'll need to define this notion of a k-deck of a string. A k-deck is just the multiset of all subsequences of x of length k. So here's an example with x, this 4-bit string 0110, and if k is 2, then I just write down all possible subsequences of length 2 and along with their frequency in the string. So 00 just occurs once, 01 occurs twice if I take the first and second, and if I take the first and third bit. Similarly, 10 occurs twice and 11 occurs once. So we just have this set of strings with their frequencies. This is known as the k-deck. And there's an equivalent way to view this k-deck as basically if I sample a random k-length subsequence from the string. So basically, if I look at a random set of size k a random subset of 1 through n of size k and look at the x values on that set, the k deck is basically that distribution up to normalization by n choose k. So why do we care about the k deck? It turns out that we can recover the k deck of a string of length n using n to the k traces of x. And this is not too hard to work out. The idea, the entries in the k deck are integers between 1 and 0 and n choose k, and it like these are non-contiguous subsequences, so they play well with the deletion channel. So it's not too difficult to see this result. So now this gives a possible algorithm for trace reconstruction from the k deck. We first recovered the k deck from the traces, and then just using this k deck, we figure out the original string. This leads to the natural question that what is the minimum k such that the k deck uniquely identifies the string. So what is the minimum k such that two different strings can't have the same k deck? And Scott in 97 and Krasigovarity independently showed that basically if k is about order of root n, then the k deck of a string uniquely identifies the string. So this gives as I said, an immediate algorithm for trace reconstruction using n to the order of n traces. Again, this is not the best thing we know, but we can generalize this to population recovery. So I'll just talk about this, the approach of this result, that the minimum k such that the order root n deck identifies the string. We'll actually look at a simplified statistic of this k deck, which is called the summed k deck. This is obtained by just considering all the elements in the k deck as k-dimensional vectors and adding them up. So for the k deck we considered earlier, the 2 deck of this string 0, 1, 1, 0, we just look at all the sequences along with the frequencies and add these up. Again, equivalently, it's the probability that if I take a random subsequence of length k from the string, what is the jth? So the summed k deck is a vector of length k such that the jth bit is the jth entry is the probability that the jth entry in the subsequence is 1 if I take a random subsequence. And in fact, Scott and Krasigovarity showed that the summed k deck of a string when k is about root n itself identifies the string uniquely. I'll show a very brief sketch of this proof because like we'll need to generalize the steps of each step of this proof in a non-trivial way to get our population recovery result. So let x and y be two strings, and let delta be the difference string. So this is a plus minus 1, 0 string, which is not identically 0. Then we'll have to show two lemmas. One is that suppose x and y have the same summed k deck. Then for any polynomial of degree k minus 1, we have this weighted sum of the values of the polynomial on integer coordinates between 0 and n times this difference vector delta I is 0. On the other hand, there is some non-zero delta for any non-zero delta which is of this form plus minus 1 0 vector. There exists a polynomial of degree root n such that this difference, the same weighted difference is non-zero. So this immediately implies that if assuming lemma 1 and lemma 2, we immediately get that there is the k deck, the summed k deck of a string uniquely identifies the string. So going a little bit more into detail into these proofs. So the first lemma is not too hard to prove. Here's the main idea. We will construct k polynomials of degree, all of them will have degree k minus 1, such that this expression delta I fi is equal to 0 for these specific polynomials. and P, these polynomials would form a basis for the all univariate polynomials of degree at most k minus 1. So then writing any polynomial as a linear combination of this, we would get the lemma for all polynomials. And the polynomials that we consider are basically constructed by counting the number of subsequences. So fix a j, fix an index in the subsequence between 1 and k, and count the number of subsequences of x which will have 1 in the jth position. That is this expression. Basically, the idea is to consider that the the jth bit in the subsequence is the ith bit in the string. Now, conditioned on that, how many ways how many subsequences do I have? And that is basically this expression. I just count the number of ways I can get j minus 1 elements from the first I minus 1 elements before the ith element, and similarly for the rest, so on. And now if I look at this product of binomial coefficients as a polynomial in I, then this has degree k minus 1, and because x and y have the same summed k deck, all of these counts will match. So these polynomials will satisfy the first equation there, and it's not too hard to show that these form a basis for all polynomials of degree k minus 1. The second proof is significantly harder. It involves construction of a certain polynomial by Borwen, Adeli, and Koch, which has this property that if it's a polynomial of degree root n, and it has this very sharp decreasing value property, which says that the value at 0 is more than the sum of the values on all integer numbers between 1 and n. So here's a graphical picture of this polynomial. So it's constructed using a certain sum of Chebyshev polynomials, which I won't have time to get into. Now, given that this polynomial exists, we can just define f to be a shift of h such that the f of 0 corresponds to the first point of difference of the two strings, and then that particular point times the value f will overwhelm all the other non-zero differences. Okay, so now we are done with the warm-up. I just will quickly describe the extensions that we do without going into details. So assume that L, the number of strings, is constant, and D is just the uniform distribution. It turns out that we can define the k-deck of a population easily using by saying that it's the weighted mixture of the k-decks of each string. So that's fine. The good news is that this k-deck can still be reconstructed using n to the k traces from the mixture distribution. However, now it's not enough to look at the summed k-deck. It turns out that the summed k-deck only determines the sum of the strings, not each string individually. So we'll need to look at more involved statistics. In particular, we'll look at, for a random subsequence of length k from my distribution, I'll need to look at correlated statistics of this form. What is the probability that, let's say, the first bit is 0 and the fifth bit is 1 and the 8th bit is 0 and so on. So it's not enough to look at just marginal distributions on one coordinate. And then we'll need to consider, we'll need to generalize the argument based on univariate polynomials that I described in the last slide to arguments based on multivariate polynomials. So I'll just state what kind of lemmas we need to prove and then conclude. So let D and D prime be two distributions over x1 through xl and y1 through yl respectively. We can, for a fixed string of length L, we consider this function, which is a function defined on all sets of size L. And it basically looks at, if I project the, if I sample a random string from my first distribution D and I project it onto some L coordinates, what is the probability that this string is C? compared with what is the probability that if I take a random string from the second distribution and project it onto the same coordinates, that is also C. And we'll need to prove a sequence of lemmas analogous to the previous sequence. So the very first thing is to show that there exists some string of length L such that this difference vector is not identically 0. Like this is not, it's easy to see for the uniform case, but for arbitrary distributions, even this is slightly non-trivial. And then we have this lemma which says that if the kdex of, oh, okay, like half a minute. If the kdex of d and d prime are equal, then for every L-variate polynomial of low degree, I'll have this kind of weighted sum is equal to 0. On the other hand, there exists a multivariate, like L-variate polynomial of degree about root n, for which this weighted sum is non-zero. And the first, the lemma 1 prime is not too hard by showing a basis for L-variate polynomials, but lemma 2 prime involves significantly new ideas. We'll need to look at the structure of delta C and argue that that attains only small number of values and so on, but I won't have time to get into that. So concluding, we show an upper bound of upper and lower bounds for the population recovery problem under the deletion channel, and I'll just mention a couple of open problems. The obvious one is to improve this gap between upper and lower bounds, and in particular also match the state of the art n to the 2 to the n to the 1/3 bound which we have for trace reconstruction, get general population recovery bounds matching that, and also characterize the right dependence on L. And also this is not computational efficient in terms of computational runtime, so we would be interested in that. And better lower bound constructions. Our lower bound constructions are very simple strings with just one in the middle. We don't know of families of strings exhibiting which are hard for this channel. Thanks.
We have time for one or two questions.
We have this model where we need to reconstruct the strings exactly, and then the distribution over them can have some error. Are you proposing that it's like you're fine with reconstructing like similar strings, like not the same strings? Is that the